very good afternoon, ladies and gentlemen, honorable guests and speakers. And good day to our friends from all around the world joining us live through the live webinar platform. A big welcome to Masterminds Masterclasses, organized by the Council of the Hong Kong Laureate Forum Limited, also known as the HKLF. My name is Marcus Kwok. What an absolute honor to be part of this wonderful event. So the HKLF aims to promote understanding and interest of young generation in science and technology, as well as to foster the exchanges among scientists of different generations, cultures, and disciplines. By organizing the Hong Kong Laureate Forum, the HKLF invites recipients of our homegrown Shaw Prize and global renowned scientists to have direct academic exchange events with selected young scientists from around the world. Before the launching of the inaugural Hong Kong Laureate Forum in November 2022, we have embarked on a series of pre-forum events to cater for a variety of audiences and to further the HKLF's mission of providing a platform for scientists with different expertise worldwide to come together to promote science and to enlighten the younger generation in the scientific community. The first chapter of the pre-forum events, namely Science Exposition, was held successfully in September and October. Today we've come to the last part of the second chapter of the Prelude, Masterminds, Masterclasses, which offers an invaluable platform and opportunity for young scientists to have an inspirational and intellectual exchange with prominent scientists. Today's session is Mathematical Sciences. What makes today's seminar super special is that one of our speakers will be joining us live through a 3D holographic projection. And I can't wait to see it myself. All right, to kick off today's seminar, let's welcome Professor Timothy Tong, Chairman of the HKLF, to give us a welcome remark. Professor Tong, please.
Good afternoon. It's good to see all of you, and thank you for joining us. As you heard, today is the third session on our Masterminds Masterclasses series. And today's seminars are focused on mathematical sciences, and the concept behind Masterminds Masterclasses is for renowned scientists to share their work, their research, and their personal journey on how to handle the highs and lows of the road less traveled by most people. The sharing aims to help aspiring young scientists to map out their own research journey and plan their science pursuit ahead. The masterminds for today's seminars are three mathematicians who excelled in different spectrum of mathematics, from numbers that transcends algebra to geometry, and algebraic geometry which span both areas. Their work has application in artificial intelligence, computing and physics, among others. Joining us on stage is Professor Mok An Ming. He is the chair professor and director of the Institute of Mathematical Research at the University of Hong Kong. Professor Mok's research interests include several complex variables, complex differential geometry, and algebraic geometry. He's recognized worldwide for his mathematical research achievements and has won many international awards. Professor Mok will give a talk on from transcendental numbers to functional transcendence. Now, I will also introduce the other two speakers before we start the seminar. But since I introduced Professor Mok, let's welcome him with a round of applause, okay? Professor Mok, welcome. And the second lecture will be given by Professor Pierre-Louis Lyon. He's a field medalist He is a senior fellow of the Hong Kong Institute for Advanced Study at City University and professor at the College de France. Professor Leon is one of the prominent experts on the theory of nonlinear partial differential equations. His work has made lasting contributions to many mathematical equations, mean field games theory, data processing, etc. His work is applied in economics, finance, plus many others. Unfortunately, Professor Leon could not join us today, but he has pre-recorded his presentation on some perspectives in applied mathematics. Although he's not here physically, but let us acknowledge him by giving him a round of applause too. Thank you. And the third lecturer is Professor Jean-Michel Bismuth. He is a recent Shaw Laureates recipient in mathematical science. More exactly, he received the prize just last year, 2021. He is joining us from Paris. Professor Bismuth cannot join us in person, obviously, but I hope you will agree that his presence in the form of 3D hologram is really the next best thing. Professor Bismuth is Emeritus Professor at the University of Paris-Saclay. His career crossed the span of two different branches of mathematics, namely probability theory and differential geometry, and ended up with the geometrization of probability. Professor Bismuth will take us through his journey from mathematics to computation in his talk on a personal experience in computation. And before walking into the auditorium, Professor Mok shared with me that he once was a colleague of Professor Jean-Michel. So I think you're joining good friend here today, although in a virtual sense. After the presentation by our three distinguished speakers, there will be a panel discussion, and our moderator is Professor Wang Yang. He is Vice President for Institutional Advancement of the Hong Kong University Institute of Science and Technology at HKUST. He's a prominent mathematician in his own right. So today, I think you are all in a session that's primed for you to be inspired, and hopefully you will aspire to be a scientist in the future. So without further ado, let me turn the floor to Professor Mok. Welcome to the floor.
It's great to join all of you here, and thank you for coming to the lecture. I want to give an impression of how mathematics is done within my research experience. And this is especially interesting for me because I started reading some book in high school, and it turned out that so many years later, I'm doing something in some way inspired and related to it. Okay, so I start with something elementary, this concept of a field. A field is something in which you can, an algebraic structure in which you can do addition, subtraction, multiplication, and division. Now, so the simplest thing is that of rational numbers, just fractions. And then there are the real numbers, and then also the the field of complex numbers. So this object I is a marvelous object. Its square is equal to -1. And this is the starting point of my research. Now, the question then comes to solving equations. One knows the quadratic formula, but in general, there's no formula for solving an equation with integral coefficients. But then one can ask, among the complex numbers, which numbers can solve algebraic equations. So this gives you the closure of Q. There are fields which are small. So there are the finite fields, Fp. This is a field of P elements, and they are also very important. When it's not, then it's of characteristic 0. And a complex field is sort of the universal object for characteristic 0 in many circumstances. And then there comes the question of function fields. A function field is simply that you can adjoin variables to this K and form rational functions, fractions. And then you can do multiplication and division and so on. So this is a function field. Now, and then there's the holomorphic functions. They are just, so to speak, generalized polynomials. So infinite number of terms instead of finite number. And then you can do calculation formally. You can, of course, introduce more variables, and you come into a conversion power series in n variables with complex coefficients. OK. Now, let me illustrate one thing about complex numbers, its importance. This is the so-called fundamental theorem of algebra. I give you an equation as written, and then the question is whether you can solve it. Can you find a root on the complex plane? Complex plane is just a real plane. And the answer is yes. But in general, if I give you equations up to degree 4, there are formulas for it. For the 5th degree already, you cannot do it. So Abel says that for degree 5, you cannot do it in general. And Galois developed what is called the Galois theory today about solving such equations. And now here is a proof of the fundamental theorem of algebra. It says that you can always solve it. And the proof goes as follows. So if P is a polynomial with no zeros, you can take its reciprocal, 1 over P. And it's easy to see that this function is going to be 0 at infinity. As you go to infinity, you are dividing by numbers that get bigger and bigger, and you get 0. And then this fact contradicts with what is called the maximum principle. Maximum principle says that the maximum is attained on the boundary. And now the boundary has value 0, so this is impossible. So this is the proof of a fundamental theorem of algebra. It makes use of one simple principle, the so-called maximum principle. Now, you know calculus, so you take derivatives. But on a complex plane, you can introduce what is called the complex derivative. So the complex derivative, so it's said to be complex differentiable if you can take this quotient and you get f prime. Now, unlike calculus in one real variable, calculus in one complex variable is very different. There is the integral formula. It says that if I have a function that is defined on a disk, on a ball, the ball is a disk, and it's defined up to the boundary, then a function can be represented as an integral from the boundary. And from this, you can derive the maximum principle. So a complex differentiable function has a way to be represented by an integral. So the boundary controls the interior. And two consequences are the following. The first is the Taylor theorem. Taylor theorem says that you can develop in power series. So it's an infinite polynomial, so to speak. The second is the mean value inequality. It says that the value at the center is less than the average on the boundary in absolute value. And this implies the maximum principle, and therefore implies the theorem of a fundamental theorem of algebra. So it looks like a statement in algebra, but this is proven by making use of complex analysis. OK, now I want to say something about elliptic curves. Now, we live on the real plane, and this can be considered a complex plane. You add a point to infinity, you get what is called the Riemann sphere. The next simplest thing is a donut. You take a donut, and the donut can be covered by the complex plane. It's C modulo a lattice. So you have a lattice there. So the lattice depends on a tau. So you imagine this plane, and you take just a lattice of points. It depends on a point tau on the upper half plane. And well, the two lattices might give you the same donut. And then the relation is given by this. This is the so-called fractional linear transformation with integral coefficients. And it turns out that there's an equivalence if you take the upper half plane, so there's a tau here, and you mod out by the SL2Z action, the linear fractional transformations with integral coefficients, and the quotient can be identified with the complex plane itself. And this is a classical function, a very important function called the J function. This just gives you a formula for writing down a function. So the J function is an expression that's explicitly expressed in terms of the lattice. The convergent series. And this gives you the J function being identifying this quotient with the complex plane. This is the fundamental domain. So if you quotient out the upper half plane by these fractional linear transformations, there is a fundamental domain, this all the way to infinity. Any point would be equivalent to a point inside there. So the quotient can be identified with this strip with a cusp at infinity. And then there's also an important function related to elliptic curves. This is called the Weierstrass P function. The Weierstrass P function is a function which is periodic with respect to the lattice. So in other words, when you move by a lattice point, you don't change the function. So therefore, it could be regarded as a function on the quotient. So P gives you a function on C mod L. A meromorphic function is something, just a quotient of two holomorphic functions. So you take two complex differentiable functions and take their quotient. And that's called a meromorphic function. For a meromorphic function can be thought of also as a map into P1. So the elliptic curve is mapped to P1, mapped to the Riemann sphere. So a donut is mapped to the Riemann sphere. I just write down something about a differential equation solved by P. This is an important equation. It says that this P, which is explicitly written, satisfies some relation. And this relation is proven by the maximum principle. So this is one simple principle. The maximum principle, the holomorphic function is bounded by its boundary value. Also is the source of this equation. And how can you describe an elliptic curve? You can make use of just the two-dimensional complex space and use two complex variables, x and y, and the equation is just a copy of this equation. So this is a certain equation satisfied by the elliptic curve. Okay, now comes to the subject of today. Well, what are transcendental numbers? I talk about algebraic numbers. A transcendental number is just not an algebraic number. If you take the complex plane, the set of algebraic numbers is a countable set. You can count them. And of course, the complex plane is continuous, and so most numbers are transcendental. But if I ask you, I give you a number like pi, is it a transcendental number? So this is a very difficult question, even to know that pi is not a fraction, it's not a rational number. It takes centuries, and it was only established in the 18th century. So in the 19th century, actually more is known, and this is Search-Lang's formulation of a result of Galfond-Schneider. Okay, now if it looks somewhat technical to you, let me just explain what is the point. The point is actually to answer the question whether pi is a transcendental number. So the answer is that pi is a transcendental number, and it comes from a theorem which says the following. K is a number field, so you can think about this as just Q, rational number, for instance. And you adjoin some functions, and you assume that at least two of them are algebraically independent, meaning that you cannot form a polynomial and get 0. And you assume also that this field, this is just a big field, this field is closed under differentiation. So for instance, you can think about the exponential function. So the exponential function, you learn in calculus, e to the power t, for instance. When you differentiate e to the power t, you just get e to the power t. When you differentiate, it's still back to itself. Then the statement says that, suppose there are distinct points on which all these functions take on, let's say, rational values, or values in k. K could be q with square root 2 adjoined to it. Then it gives a bound. Actually, there are only so many points, at most so many points. And the answer to, and this gives you the following most important thing, that e to the power alpha is not going to be an algebraic number if alpha is a non-zero algebraic number. In particular, e itself is not an algebraic number. I guess that the proof is not so important. It simply says one applies this theorem. You essentially look at functions which consist of z and e to the power z. So, and also pi is not an algebraic number. So this answers, well, in a question from antiquity. Pi is not an algebraic number for the simple reason that e to the power 2 pi I is equal to 1. So if this were an algebraic number, the statement would imply that you have infinite number of algebraic numbers taking of 4 pi I, 6 pi I, and so on would be equal to 1, and therefore you have a contradiction. This is another similar theorem. It says that the power alpha to the power beta is a transcendental number. Well, these are fascinating facts which are difficult to prove. And in order to prove them, one uses very clever construction of functions. So here is the argument. So, but in mathematics, you do proofs. I'm a pure mathematician. And when you do proofs, you start with basic principles. And there are some very simple basic principles which turn out to be the key. The first principle is the so-called pigeonhole principle. You have so many pigeonholes, and you have so many letters to be put in the pigeonholes. If you have more than the number of holes, 2 of them must sit in the same hole. As simple as that. And this is a key, one of the 2 keys. And the point is that if you look at, it's applied to this, you have a system of linear equations like this, a system of linear equations, and you have more unknowns than the number of equations. And then it says that you can find these solutions xj which are sufficiently small so they can be estimated. This is, of course, only applied to rationals, but you can apply this to number fields. The other basic principle is the Schwarz lemma. The Schwarz lemma says that if you have a function which vanishes at the origin to a certain order, so like z to the power s, it vanishes to the second order, then you can estimate its next derivative, so the s derivative, in terms of the radius and in terms of some explicit thing, and then the maximum value along the boundary. So this just comes from the maximum principle. So one basic principle, namely the maximum principle, applies to give you this. So in transcendental number theory, what one does is to construct auxiliary functions. You take this f and g, these are functions among the fi's, and you form a polynomial. And you look at this coefficients aij. Now you take the aij as unknowns, and you try to find aij sufficiently controllable so that you can make use of this function. The controllability means here that you want to make sure that the derivative of the function at a certain number of points are going to vanish. Now then you apply 2 things. One, you have estimates on the coefficients. You have estimates on the coefficients, and therefore you get a lower bound. So you take a point where this is going to be non-zero. Suppose I work with rational numbers. So then there's a fraction. A fraction, you can look at the denominator and the numerator. The denominator is also an integer. So there's one fact, one salient fact. There is a smallest positive integer, namely 1. So therefore, when you express this out, it is possible to say that this is at least how much whenever it's non-zero. And the other thing is at most how much, because this is a certain derivative, and you know the functions are of finite order, like exponential function. And therefore, you use the maximum principle to get an upper bound, and you use the just the pigeonhole principle to get a lower bound. And the two bounds would contradict each other if the number of points where they take simultaneous values in Q, for instance, is too much, is too large. So that therefore, contradiction arises when the number of simultaneous points is too large. And therefore, you get the estimate. Okay, so this is a theorem of Schneider, which just says that if you take the J function, then the J function takes simultaneous algebraic points only at certain very particular points. Now, this is the famous Lindemann-Weierstrass theorem. So it says that if you take e to the power alpha 1 and e to the power alpha n, then they are algebraically independent, provided that these algebraic numbers are independent over Q. And this is the famous Chanuel conjecture. Chanuel was a student of Search-Lang's. It says that if I take a certain number of points, they are Q linearly independent, and you take the exponential, then these two n numbers must have the transcendence degree at least equal to n. So Baker was Fields medalist in 1970, and his work is well, in a way, answers this in some very special case, and this consists of taking logarithm. Now, then this is Bombieri's work, Fields medalist, actually after 1970. He just generalized to several variables, the same theorem, but several variables. And I want to add something. How do you go from one variable to several variable? And this is done by making use of solving differential equations. And this solving differential equation is to solve the equation d bar u equal to f. You want to solve this equation. F is given, f has certain growth, and you want u to be estimated. And this is a famous work in the partial differential equation, linear equations. So there's another additional ingredient, which is the beautiful work of Pierre Lelong, and it's a notion of a current. The most important point here is that in more than one variables, I give you a function phi, you can compute, this is called a complex Hessian. And so this is the complex Hessian, and its positivity is very important for solving differential equations. Okay, so what he did was that when you look at the ratio of the mass of a current and compared to the volume of a ball, then there's monotonicity. And this was a key point in the proof of Bombieri's result. And this is work of Yam-Tong Siu, my former supervisor, who's a graduate from Puijing. And he proved this deep structural result about closed positive currents. And this is just to say that there are certain tools in several variables that one can use to work in several variables. I would now simply go to one key slide. I want to. Okay. Now, in several variables, so I was talking about the upper half plane, this H. So the points where tau and j tau are both algebraic are called special points. So these are the results from Schneider I mentioned about. And now the Andreault conjecture, so these are the special points. You can define special points also for higher dimensions. For instance, this can be a ball. And then there's the so-called Andreault conjecture. It says the following. If you take, this is like, in one variable, this would be just the H mod SL2Z. And this would be the complex plane. But in general, you have high dimensional picture. The conjecture says the following. If you take any set of special points, and you take the smallest algebraic set which contain these special points? The answer is that they are union of what one calls special subvarieties, and they are totally geodesic subvarieties. And what makes differential geometry relevant to this problem, apparently a problem in number theory, was the so-called Pillar-Zanier strategy. This strategy says the following: in order to solve the André-Odd conjecture, one can reduce it to two problems. One problem is algebraic number theory. So this algebraic, and the other is differential geometry. The algebraic side is to look at the orbits of under Galois group, so the very Galois that I mentioned at the beginning. And then the other part is to look at the size closure of algebraic sets. So algebraic sets are easier to handle than algebraic numbers. So this is the theorem. The theorem says the following. This is a theorem of Klingler, Ulmo, and Yafayev. It says that if you take omega to x gamma, and you take a certain algebraic set, so this takes the place of algebraic number, you take its quotient, and so it sits inside something algebraic, and then you take its Sarisi closure, the smallest algebraic set containing it, and what you get is something which is algebraic. Quasi-projective means algebraic. So my entry into this, okay, so I was just trying to mention what are things that can be used to it, and the proof actually consists of making use of a counting argument in logic, actually. And then another part of this is an argument. So this is the logic part. And the other is the monotonicity formula coming from Lelong. I mentioned it. And this allows the lower estimate to be obtained. So like transcendental numbers, there's an upper estimate and a lower estimate. And these two can be put together to get the theorem. So well, because this is just to say that all this formula can be obtained by doing calculus. If you are in university learning calculus, you know that there's a Stokes formula, and it's proven by using a Stokes formula. Okay, so I will not go through it. I will just finish with stating one theorem. So this is a theorem of mine, and it comes out as, well, philosophically, as the new addition to the arguments, namely I'm making use of complex differential geometry to do this problem related to the André-Odd conjecture. And the final result is the following. Okay, so this is just a theorem. So this is very recent work that I collaborated with Piller and Zimmermann, Piller at Oxford and Zimmermann at Toronto, where we prove the Ax-Chanuel theorem. The theorem, when it's stated in this way, might not see what it means, but I will give you this formulation. The formulation is this. I take omega to be a bounded symmetric domain, take V to be a complex analytic subvariety. So it's defined as zeros of certain analytic functions. And then you look at the following functions. This looks like the J functions. This is the analog of the J function. These are the Euclidean coordinates. So you have altogether n things here, and, well, a number of them, so the so-called generators of automoic forms. The statement is the following, that the transcendence degree of this field of functions is bounded from below by n plus dimension v. So if you forget about this dimension v, this looks like exactly like the Chanuel conjecture, and that's the reason why this is called Ax-Chanuel conjecture. This extra dimension can also be explained. So this looks formally like the Chanuel conjecture. And it formally looks like that, but the proof, well, how is the proof related to attempts to tackle problems in transcendental number theory is rather on the methodology. So the methodology of using complex functions, of using L2 estimates and so on, are actually related in the two sides. But the logicians have been working on this. Number theorists have been working on it. And I was working on it by introducing my use of algebraic geometry and differential geometry, and the works together finally came to a solution of this well-known conjecture. So let me stop here.
Thank you very much, Professor Mok. That was absolutely phenomenal. Thank you very much for the presentation. Now, okay, here's time for Q&A. Shall we take the first question from online first? Here's the question. It's quite long. Let me read it slowly for everyone. As I believe, all application is based on pure mathematics. Is there a case that your pure maths finding was used by someone to develop application? What did you feel?
Well, I started my career working in complex analysis. Then I worked on differential geometry. So I was at Columbia. So I was at Columbia, and I was a recipient of the Presidential Young Investigator Award. And in a meeting of the awardees, an engineer came up to me and asked about the questions in Riemannian geometry. So Riemannian geometry is differential geometry introduced by Gauss and Riemann. And it turns out that Riemannian geometry is now used by the investigators with background in science to model certain constructions in engineering. So I would not say that what I do directly applies to real-life problems, but the range of expertise that I was working on and I was competent in actually find their applications in different questions. So I could also say, for instance, if you look at elliptic functions, so elliptic functions are studied by many, many different people from many different angles. And when they study it, they wouldn't know that actually elliptic functions are made use of in cryptography. Yeah.
All right. So you can keep that, Professor Mok. Okay. Next question, we will take you from the floor, a live audience. Yes, this lady over here in the third row.
Thank you for sharing. So you just mentioned Stokes' law. So I'm curious whether there are any other application of Stokes' law, because I've heard of it and used in other fields as well. Thank you.
Other applications of the
Stokes' law.
Of what I talked about, or
Stokes' law in particular. Stokes' theorem.
Stokes' theorem.
Stokes' theorem.
I didn't quite hear.
Stokes'
theorem. Okay. Oh, Stokes' theorem. This integration by parts argument. Stokes' theorem, for instance, was the when you study PDE, on domain with boundary, and this occurs, of course, in many real-life questions. Stokes' theorem allows you to transfer the integration in the interior to the boundary. So, for instance, this is how the L2 estimates of Hermander was done using the Stokes' theorem. Of course, it involves much deeper analysis, but this is a basic thing. I want to show the Stokes' theorem because people are sometimes afraid that in order to do pure mathematics, you need to use very sophisticated tools. But even very sophisticated tools are grounded on very basic things. Stokes' theorem is just fundamental theorem of calculus, just in 2 or more variables. Okay, so again, the other example I was mentioning, like maximum principle. So maximum principle can also be proved by using some analog of Stokes' theorem. So very basic things come from fundamentals, and the fundamentals must be well grasped if you want to do research.
Thank you. Thank you for the great answer, Professor Mok. And that's all we have time for Q&A for this part. And thank you very much, ladies and gentlemen, Professor Mok. Professor Mok, we'll invite you back again for our panel discussion a bit later. Please have a seat and continue to enjoy our program today. All right, for our next presentation, we have a pre-recorded presentation by Professor Pierre-Louis Lyon. He's a professor at the Collège de France and École Polytechnique and was awarded Fields Medal when he was under 40. The Fields Medal is regarded as one of the highest honors for mathematicians and has been described as the Nobel Prize of Mathematics. Professor Leong has a strong tie with Hong Kong, as he is also a senior fellow of the Hong Kong Institute for Advanced Study of City University of Hong Kong. He said he very much wanted to return to Hong Kong and attend this event in person. But we all know that traveling isn't that easy these days. But Professor Leong still managed to record his great presentation for us all. So ladies and gentlemen, please enjoy.
Hello, welcome to the Hong Kong Laureate Forum. First, I need to apologize for not being able to participate in another way than recording this brief presentation. Some serious familial constraint makes it impossible to do otherwise. So what I want to do today is share with you some thoughts about what's happening in mathematics, and more precisely in applied mathematics. So in particular, it's not going to be a technical presentation. Don't worry. There won't be too much math. In fact, there will be very little mathematics, and certainly absolutely nothing technical. I'll begin with a little bit of blah blah, a few facts, some introduction. The terminology is a little bit vague. Applied mathematics, what does it mean? I'm not going to attempt to define it. Instead, what I want to say is that I want to show how much mathematics are invading our everyday life, and this goes through the applications of mathematics and applied mathematics. So instead of trying to make some kind of abstract definition, I want to emphasize a few points. So let me begin, because we are discussing mathematics, with one of my favorite quotes by one of my favorite mathematicians, John von Neumann. In my eyes, he is one of the most important mathematicians in the 20th century. And he said once, one never understands mathematics, one gets used to it. Okay, never understand mathematics, one gets used to it. So relax if you don't, if you didn't understand everything in your mathematical classes. It's normal. One needs time to get used to it. In some sense, attempting to define applied mathematics is meaningless, because mathematics were built by humankind. Mathematics were built, as I was beginning to say, for understanding the world around us. And to make my point clear, I want to say a few things about the etymology of the various words that appear in mathematics. For instance, if we think about analysis, analysis comes from the Greek, and in fact means to decompose a problem in small pieces before reconstructing it. And think about what people do when they analyze something. That's exactly what they do. Algebra comes from the Arabic a little bit later. And there is this idea of balance, balancing things. And some of you, I'm sure, have had some difficulties with algebraic equations at high school, where you have, you know, those x plus 2 multiplied by x minus 18 equal whatever. This is typically, every time you do a manipulation, you have to keep an equality, you have to keep the balance. So this goes back to the Arabic. Even more striking is the words that are related to probability theory. One word, a word that is really common language, is hazard. Hazard. There is another word for randomness, at least in Latin languages, which is aléatoire. aleatorio in Italian or in Spanish, and so on. And hazard comes from the Arabic and means dice. Alea comes from Latin and means dice. So the dice, of course, representing something which is essentially random. You throw the dice, you don't know which number is going to pop up. And so in both Arabic and Latin, you have the same modification of the meaning of the word, in the sense that it started with dice, then it became the way you sent dices, and then it became the science of what we call nowadays hazard, and that's what we call, in modern language, probability theory. Of course, there has been many, throughout the centuries, there have been many landmarks which, in the 19th century, there was an acceleration using more and more equations, more and more complicated math, but it was always to try to understand something around us. At the late 19th century, appeared some maths which were supposed to be very abstract without any applications. But in fact, we realized a little bit later on that the applications were there, not present when the maths were invented, but they came later. So that's a general lesson, is that there might be some aspects of maths which nowadays look completely useless, but you never know. It may change in the future. Of course, in our era, what we call the digital, I don't like the word digital, prefer the word numerical. With the numerical era, you have maths all over the place. Okay, so in some sense, I would like to say that nowadays applied maths are essentially what I would call contemporary maths. While classical maths, more theoretical maths, should really be considered as classical maths. Think of classical music, and applied maths being all the modern music you may like or not. Of course, I'm an applied mathematician, and that's the kind of music I like. So indeed, mathematics are all over the place. You take transportation, you take a car, there is mathematics, or a bus. You take the subway, you take a plane, you take a train. There is math all over the place. You listen to music with a CD. The information is compressed by a mathematical standard. And so on and so on. There is really mathematics all over the place. Plus, you're all aware that nowadays people are interested in massive sets of data, and all the algorithms are mathematically based. In fact, if you use Google search, behind the algorithms of Google search, you have a mathematical theorem, Pierron-Frobenius theorem. So you have maths absolutely all over the place. Doesn't mean that you have mathematicians all over the place. That might be dangerous, but you have mathematics all over the place. So what I want to mention, I'm sorry because it's going to be my story, my experience, but I just want to show you a few personal, recent examples. So they have value for me, and they are just examples. And that's hence the warning that I put on the second line of that slide. These examples may not be exemplary. It's just examples that I like. And the reason why I'm mentioning those 4 topics, it's because you might not expect mathematics or mathematicians like I to get interested in such problems. So those 4 topics, and don't worry, I won't get into details, are mobile telecommunication networks. I indicated a group of researchers, which is a mixed bunch. I mean, two of those guys are engineers. In fact, they are engineers in the big telecommunication company that is, I'm sure, quite well known in Hong Kong, namely Huawei. We've had quite an extensive collaboration, research collaboration with the Huawei subsidiary in France, Huawei France. And Debat, the second name, is in fact the guy who was in charge of all research in Paris for Huawei. Charles Bertucci is one of my former students. Jean-Michel Lasserie is a collaborator. Mobile telecommunication networks. I'll come back in a minute. Why mathematics there? It's in fact telecommunications is all over the place. Is full of math. More surprising, math for Bitcoin mining. Okay. Machine learning, I already explained that the algorithms may have something to do with, I already mentioned that many algorithms may have something to do with math. Oil production, how to model oil production, and again, it's in applied mathematics projects, it's always a mixed bunch. Rostand is the head of a startup company on oil data. José Schenkman is a famous American-Brazilian economist. And all those things are related to Minfield games, which is a mathematical theory we invented with Jean-Michel Lasserie already some more than 15 years ago, and a large group of collaborators, and I just indicated the names. I really don't have time to go into the details. You have the transparency if you want to read it slowly and carefully. Let me just summarize all this mess, all this messy slide, by saying that Minfield Games models are a mathematical way to describe the behavior of a crowd, of a large number of agents, of players, okay? So it's clearly what we expect to find in an economical, macroeconomical situation. Let's say the economy in Hong Kong, well, all of you are actors, agents in such a situation. So you have to think of a large number of agents, players, which can choose what they do and which interact with each other. And of course, what the others do influence what you do, okay? So this is also what's happening in social networks. It's also what's happening with large amounts of data involving human people. It's what happens in telecommunications network, because typically we expect around to have millions of connected devices in a square of an area, let's say of an area which is about 1 square kilometer. So there is no way you can run, when you have such huge number, there is no way you can run it in a centralized way, in a pyramidal way, which was usually the case with the telecommunications network. Intelligence has to be spread out. Lots of local decisions, and of course you have to make sure, and they interact because they are sharing the resources, and that's something that it's very natural to attempt to make models of that through these Minfield Games models, which precisely want to describe situations which involve a huge number of players. There are many, many applications of Minfield Games. I mentioned a few. In fact, we started this Minfield Game theory because of applications to sustainable development. Clearly, those are situations where you have lots of actors and lots of interactions. Okay, so this leads to a very complicated math that I won't be, that I don't want to describe. But as I said, it's the mathematicians have tried. Our group, for instance, has tried to provide a toolbox that allows other people or ourselves to study particular problems. And the 4 examples I gave are precisely examples where you take the theory, the mathematical theory, and specialize it on a very specific problem. Okay, let me instead of trying to detail the example 1, let me describe instead the example 2, which is a very simple, S is for simple, which is called in English the Mexican wave. In Europe, it's called the ola. You know, that's where you go to a sport event in an arena, and you well know that from time to time, people in the crowd, you know, suddenly stand up, push their hands up, and this creates a wave that propagates, okay? And it's an amazing phenomenon because there is no one is centralizing there is no one which gives the order. It's slightly silly. No one is being paid for it. It's completely spontaneous and it's organized quite well, and it can be pretty stable. So we provided. I don't have time to explain it. We provided some kind of mathematical explanation of what happens. And we made a prediction, is that basically you should expect to have always the same speed out of the model, the same speed for the wave. And it turns out that that has been observed. All the olas worldwide go to the same speed. So I don't have time to describe how from you make a mathematical model out of that. I wanted to mention this prediction, not so much to say, well, we have the good model for the Mexican wave, but to explain what you can expect from models, making predictions, understanding what happens, and so on. Okay, so about the recent applications, and I will stop after describing these recent applications. The mobile networks, I'm coming back. What is a crowd? That's a crowd of devices which are connected to an antenna, okay? That's typically a 5G situation. In the 6G, the next generation, in the 6G, what I'm saying is even more complicated because of the number of devices and so on. And that's some of the things where we are thinking about models to improve the 6G, which is, let's face it, essentially ready. But we are not ready for what comes after the 6G. This seems a little strange because right now in the world, we are just developing the 5G, but the 6G is ready. And so one crucial aspect for the future is to minimize the energy that we use in the devices. Clearly, our phones can do more and more stuff, clearly. But whenever they do something else, I'm calling, and of course, excuse me, and of course, even if you make a call, you use energy. And the problem is that you don't want to run out of battery after a few hours. You want the battery to stay alive for, let's say, 1 day. That's a minimum. So this issue of minimizing the energy usage, on one hand, it's good for the environment, and on the other hand, it's also absolutely crucial. While, as I just said, you expect to have more and more intelligence in your device. More and more intelligence means consuming more and more energy. So this is that's why you need to optimize everything else in order to minimize the energy usage. And you need, in order to optimize, you need to make some kind of mathematical models. Bitcoin mining, in fact, that's part of a big project we have on cryptocurrencies. The crowd are the miners, and clearly there is a competition between miners, let's say in a proof of work based blockchain. So if you don't know what the blockchains are, if proof of work is, don't worry. One more, it's about the energy which is being consumed, because as you know, mining, Bitcoin mining can consume a lot of energy. So can you think of other types of blockchains? How is it related to the progress in terms of computer power and so on? I mean, those are the questions we tackled. And there are things which are called lightning networks, which are even more complicated and interesting. I don't have time for that. Machine learning, in fact, we are developing mathematical models with mean-field games for machine learning. And we are also using machine learning to solve mean-field games. My last example is about oil production, which is really trying to have a model which describe what may happen with in the production of oil, gas, shale gas, etc. So this is a situation where there is a crowd of producers. There is a major agent, which is like a cartel. That's what we call in France OPEP, that's this federation of big producers like Saudi Arabia. You have small producers, a crowd, and you have also another crowd, which are arbitragists that store oil. So two crowds are major agents. They are mean-field game models that have been calibrated on historical data and which are in perfect agreement with the production shares. Let me tell you that story because when we finished, when we were on the verge of finishing our work, we got worried because we were getting informations. That sounds strange for us. One was a phenomenon that we call the cliff, is that in certain circumstances, the oil price would fall dramatically, which was a combination of high stocks, low demand, and a very violent move of the prices. And even worse, we observed in our numerical simulation some negative prices. And so when we saw that, you know, mathematicians, you have to make a model, but you have to believe your model. And if you see something strange coming out of the model, what you've done may be all wrong. So we started consulting experts. The cliff, people said, it's there. We have seen it. Don't worry. Okay. What about negative prices? Well, on March 23 of the beginning of the COVID crisis, there was an article in the Financial Times, which was hugely read, quoting our preprint, which was circulating, saying that the current oil crisis was explained by our games theoretical work. We were very happy with that. And even better, in April, negative prices were observed. So that's, you remember the COVID crisis starting, well, depending in which country, but in Europe, it started in March. And by April, negative prices were observed for some oil futures. Well, okay. So I want to insist upon the fact that mathematics is an incredibly powerful tool, but you have to check what you do to make sure it corresponds to reality. What may happen next? That's my last slides. Well, clearly, more and more mathematics are going to play a role in very important societal themes like environment, climate destabilization, energy, resources, water. That's completely obvious. There are various initiatives worldwide, and in particular in Paris. I don't have time. So I mentioned telecommunications. I mentioned artificial intelligence and data sciences. Well, let me mention that when we, maybe 10 years ago, we had a startup company called Minfield Games Labs. About 6 years ago, we sold it because it had grown too much, 50 people and so on. That was not fun. It is still a high-tech company in France. And our goal was to use Minfield Games models for data sciences. And we had a major success in the movie industry, and we sold it because it was getting too big. Medicine and biology, during the COVID crisis, we all have heard epidemiologists using mathematical models, statistics, and so on. And this is going to grow a lot because I'm worried about the future because of the environment, because of the human activity, and because of the implication it will have also on our health. So this, I'm sure, is going to be also, oh, I'm sorry, it's going to be a very hot topic in the future. And my point is that there is a need for mathematical understanding for all that. You may use some mathematics without really understanding. That's what happens very often with machine learning. One uses some kind of black box, it gives results. But there is a need for mathematical understanding to do better, but also to be fair, in the sense that think of machine learning, you may have algorithms that decide about your life. So you certainly want those algorithms to be fair. So that doesn't make any sense. An algorithm cannot be fair or unfair, but it's the way you train it. It's the type of example you use to train your neural networks. That's where fairness lies. And that's a complex thing. And if you don't understand what's going on in the neural network, there is no way you can guarantee some kind of fairness. So both for understanding, for doing better, for improving, but also to respect human people, we need more mathematical understanding. There is already mathematics all over the place. It's going to grow, but we also need to work hard to try to understand what the mathematics and the algorithms are doing. So that's why I strongly advocate models, simulations, and also analysis. Of course, I'm completely biased because that's what I love to do. I just believe it's relevant. And at least I'm sure that there will be young people listening to that. Important, that's a big word. Relevant, that's also very serious. But believe me, it's fun. Well, I guess that I just need to thank you for your patience, and I just hope that you will enjoy very much this forum. Thank you very much.
Thank you. Thank you, Professor Leon. We really appreciate your effort, even though Professor Leon was not able to be with us live, but he still recorded that great presentation for us, especially for us. So for our next presentation, we will have our 2021 Shaw Laureate in Mathematical Sciences, Professor Jean-Michel Bismuth, joining us live from Paris. Now, Professor Bismuth is an emeritus professor of mathematics at University Paris-Saclay. So ladies and gentlemen, please welcome Professor Bismuth.
Okay, so thank you very much for the introduction. I'm very happy to be here in spite of the fact I could not come to Hong Kong for obvious reasons, but I hope at least that I will be able to convey something. So the title of my lecture is actually inspired from a short novel by a well-known German writer, 24 Hours in the Life of a Woman. What I want to describe here is just one day in my life as a researcher which changed my way of doing mathematics because, in some sense, I exactly obtained on that day what I was dreaming about. So obviously, I will not explain the problem in detail. There will be many undefined things. Sometimes just take the pictures as they are. But I hope at least to give some of the excitement one can have when doing mathematical research. So first of all, I introduce a well-known function, probably the most well-known function in the world, the Riemann zeta function. And it's the sum of the n to the minus s. So this function has a lot of properties that I will not explain. Let me just say that it takes, in particular, rational values at odd negative integers. Now, I introduce another function, that the so-called a roof of x function. So it is given by this seemingly innocuous formula that's x over 2 divided by the hyperbolic sine of x over 2. And again, that's a function which appears in many branches of mathematics, in analysis, in probability, and also in algebraic geometry in connection with a well-known theorem, the theorem of Riemann-Roch. I won't tell you what Riemann-Roch is, but I just give this formula for the a roof of x, which you can write as an infinite product over the integers. This infinite product in the denominator, you can eventually interpret it as an infinite determinant. And as you know, determinants come in when you compute Gaussian integrals. And actually, the reason why this function a roof of x appears in analysis is exactly because of that, because it is, in some sense, its inverse is an infinite determinant. So you can do the following computation. You can take the log derivative of this function a roof of x, write a prime divided by a roof of x. The log derivative of a product is a sum. And if you do the computation reasonably, using also the so-called functional equation for the Riemann zeta function, you get this expression here, an infinite sum involving the values of the Riemann zeta function at negative integers times x to the power n divided by factorial of n. Now, let me describe another series which was invented by my collaborators Christophe Soulet and Henri Gillet. So, in joint work with Don Zagier, a number theorist, and with the help of uComputer, they come up with the following power series, which superficially looks like the previous one, but now what you have, you see appearing derivatives of the Riemann zeta function at negative integers. And the way this power series appeared was because they were trying to compute a certain spectral invariant, an invariant which depends on the eigenvalue of the Laplacian, on all the possible projective spaces. By putting together these computations, and with the help of a computer, they came up with this series R of x. What is strange about this series, for people who know about these things, is that you have derivatives of the Riemann zeta function. So let me briefly explain the problem I was trying to work on. I decided to work on a problem combining analysis and geometry just on a single manifold, on a single complex manifold, compact complex. And I was trying to study the behavior under embeddings of this sort of spectral invariant. Spectral invariant, again, means invariant depending on the eigenvalues of the Laplacian. That's the behavior of this spectral invariant that's called analytic torsion. Conjecturally, So conjecturally means that in principle, if the work was well done, Gillet and Soulet had conjectured that the full function R of x, the previous one with the derivatives of the Riemann zeta function, was supposed to appear by an explicit, local, analytic computation. Analytic means just using the tools of classical analysis. But where would such an expression come from? Why would they be derivatives at negative integers of the Riemann zeta function? I was then on the verge of despair, literally, not knowing where would this function come from. But then I decided to build a strategy. So I reformulated the problem I had, which was to study the behavior of the spectral invariant analytic torsion and embedding, as a problem of geometry about intersecting two objects in a certain loop space. So loop spaces are just a set of loops you can build on our classical space or on a manifold. And I just give you the example here. If you don't get it, it's not too important. So if I have y embedded in 2x, I just look at the intersection of the loop space of y intersected with x. And this intersection is just the manifold y, the trivial loops. The problem of this intersection, it is that it is non-transverse. So I will try to give a hint of this what this non-transversality means, but my guess in the strategy I had devised was that the Gillet and Soulet function R of x should be obtained by cleverly computing the intersection of these two non-transverse objects. So let me just make a drawing to explain what non-transversality is. I wrote here the intersection of two lines in R3. You have D1 a first line, D2 a second line, and they are not transverse because in some sense they do not span the full space. There is a so-called excess normal bundle, this line up there. These two lines do not span the full space R3. And this is eventually a bad situation because it's extremely unstable. If you take these two lines and disconnect them, they don't intersect anymore. So in some sense, I had understood the problem I was working on was related to this instability. So let me explain how I came up with a solution. First of all, I introduce the following function, psi of u and x. You do not need to literally understand what it is. Let me just say that when you take the value of u equal to 0, you recover the function a roof of x. And now the second fact that you should know is that, again, the function psi can be written as an infinite product over the integers. The product is slightly more complicated than before. So here is a function. Again, you do not need to look literally at what the formulas are. I introduce a function c of s and x, which is a so-called Mellin transform, that the name, there is a formula with gamma of s in denominator. It doesn't matter. And you see appear in the integral, again, the log derivative of the function psi. My guess was that the function d of x should be closely related to the function r of x. I had obtained this function d of x by cleverly computing the intersection of these two non-transverse spaces inside infinite dimensional loop space. That was my guess. that evening, an evening around 1988, I called my collaborator, Christophe Soulet. I gave him the formula I showed you before for the function d of x and begged him to compute at least the first term in the expansion of d of x as a function. The reason why I begged him was that I was literally exhausted. I had been working on the model, on a strategy for 6 months. I had come up with this function, and I told him, if the function zeta prime of -1 does not appear in the first term of the expansion, I will quit mathematics. This was for me a very dramatic evening. I was too tired to do the computation myself. So the next day, that's where the 24 hours come in. The next day, Christophe Soulet called me very early. And he told me that the first term, which was a factor of x, contained exactly 2 zeta prime of -1, as was conjecturally anticipated. And then we immediately computed the remaining terms. This was an extremely exciting moment for me, because that was the moment in which my model of the mathematical problem was meeting, in some sense, the conjectural computations done on a computer. And here is the result. The function d of x is not exactly given by r, is not exactly r of x. There is just an extra factor, gamma prime of 1, so that, in effect, the function d of x is almost equal to r of x, up to an irrelevant factor that I had already anticipated. So this was for me the very day where effectively my theoretical understanding of a problem met the experimental computations of my collaborators. And they literally met, and I knew that I was on the right track. So the final computation, the conclusion, is that the original problem of analysis was that I wanted to solve had been reformulated by me as a problem of infinite dimensional geometry. This problem was solved using this geometry. The corresponding local analytic objects were eventually understood and constructed by me, and later the original problem was completely solved with my collaborator Gilles Lebeau. So I give here the 3 relevant references, and I thank you very much for your attention.
Thank you very much. Big hands for Professor Bismuth. Professor Bismuth, so great to have you with us. Can you hear us? Professor Bismuth, so great to have you with us. That was phenomenal. And I'm sure that inspired a lot of our viewers to ask questions too. We have time for Q&A. We're going to take one question from online and one question from our live audience here. That's okay. All right, the first question is from online. What is the next question in maths that you would like to solve?
Oh, there are many.
I'm sure.
There are many. There are many more questions I would like to solve than the ones I will have time to do. So basically, I mean, you know, I started as an analyst and probabilist, And basically, we have moved progressively trying to do more geometric analysis on infinite dimensional manifolds. This is difficult for many reasons. There are many things which do not make sense, however much you try to make efforts with, and still the conclusions you draw from these objects are often correct. So what one would like to do is build the proper theory in which we could do geometry on infinite dimensional objects like the loop spaces, the loop space being just a relatively simple model, and that for the moment we cannot do. It's very difficult, for instance, to make sense of infinite dimensional partial differential operators. There's been, in that respect, remarkable progress by Martin Herer, who is a probabilist, who succeeded finally making sense of a number of this kind of object in a special situation. There are many other problems in that direction.
So there you go. That's the answer from Professor Bismuth. Okay, now the next question we're going to take from our live audience here. Who has a question? Just put your hand up and our lovely staff will pass you the microphone. Don't be shy. This is a great opportunity. Anyone? Yes, we've got a question.
Professor Bismuth, thank you so much for your sharing. And I'd like to know that for your very dramatic and exciting night, were you very confident that your collaborator will be able to get your first term that you thought you would get? Thank you.
Yes. Yes. I mean, the computation which remained to be done was easy. I try to explain to you because you have these log derivatives of a product. That's an infinite sum. And that's a sum over the integers. And so basically you're back in the formalism of zeta function in some sense. So I knew the computation could be done, but at that day, at that evening, I was simply not able to just to write anything. I was too tired. I was absolutely too tired. So I told him, please, do the computation and call me if the 2 zeta prime minus 1 appears. And he called me and it was there. And not only that, but we got basically all the terms that had been obtained by putting together scattered computations with a computer. I produced this series, and this series was just produced by my own just mind, by having the proper model in some sense, which will produce everything. So it was a life defining it was life defining in the sense that, it was either it would be this or it would not work. And I had told him that if this did not work, I would leave mathematics. Now, I'm still doing mathematics. So that means that one can be on the optimistic side. But I want to say that research can also be a very dramatic, extremely intense sort of situation, because you're dealing with complicated problems where you do not know where completely you're going on. And then when there is this piece of verification, concrete, explicit, that's extraordinary.
Thank you, Professor Bismuth. Very interesting and a very satisfying face from our student here. We would love to hear a lot more from you, Professor Bismuth, but unfortunately that's all the time we have for Q&A session, this part. But please stay with us. Please stay with us because we are going to invite you back very soon for panel discussion.
Thank you.
So just bye for now, just for a few seconds. All right, now I'm going to proceed to this side of the stage because we're going to have a panel discussion very, very soon. I'm going to share a little story about myself. When I was in primary school, I used to hate maths. I thought, after division, subtraction, multiplication, percentage, what more do we need to learn? Is it really useful in our life? And little did I know that maths actually can help us, our brain, to think more analytically, more logically. So it sort of build a foundation for our brain to look for solutions and solve problems. So that's very, very useful. So it's not surprising when you come across someone who is very good at maths, you automatically associate that person as being very smart. So there you go. If you want to be smart, learn maths. That's just my 2 cents. All right. Okay, now it's time for panel discussion. First, we would like to invite our moderator for the panel discussion, and that is Professor Wang Yang. Professor Wang is the chair professor of Department of Mathematics and Department of Industrial Engineering and Decision Analytics of the Hong Kong University of Science and Technology. He's also the vice president for institutional advancement and director of HKUST, the Big Data for Biointelligence laboratory of the university. So, very welcome, Professor Wang, and also we would like to invite Professor Mok to the stage for a panel discussion. Welcome again, Professor Mok. And of course, we have Professor Bismuth joining us live from Paris. All right, Professor Bismuth, can you see us? Can you hear us?
Yes, yes.
Fantastic.
Yes, I can see you, yes.
Fantastic. All right, now it's time for panel discussion, and I shall pass the time to our moderator, Professor Wang.
Thank you, thank you. It's been a great forum so far. So my name is Yang Wang, as introduced, and in the time of interest, we will, we don't have a lot of time, so I'm going to start off with a very light-hearted question to Professor Bismuth. I actually saw in your biography that when you first entered university, you were, you were just a 19-year-old, I guess, at that time, and your first mathematics course was taught by Professor Laurent Schwartz, a Fields medalist. I had this wow reaction. Okay, so I want to just you to tell the audience, were you intimidated as a first-year young student? Did it inspire you? I mean, what kind of how did you feel at that time?
Well, of course I was intimidated. Laurent Schwartz was a great mathematician, but he was also an extraordinary teacher. And so he could give these lectures of 1 hour, 2 hours, flowing like this, extremely clear, so easy to follow. So this impressed me a lot. But what also impressed me very much was the fact that he was genuinely interested in students. He organized a seminar in late evenings, as far as I remember, starting 8 or 9 in the evening, lasting 2 hours, and this maybe twice a week. This was just unbelievable. He was distributing fields to talk about, and certainly my first serious mathematical training came from him.
Yeah. Okay, thank you, thank you. I think, I wish I had experience like that. I think many of our students certainly would feel the same way. My next question is to Professor Mok. So let's go to our current situation in Hong Kong. As an educator, as a mathematician, I have also been involved in recruiting students into the university and teaching math courses. What I have noticed is among high school students in Hong Kong, fewer and fewer of them are taking advanced math modules, M1, M2, or other kind of advanced math material. In fact, I remember when I first came in 2014, when I first came to Hong Kong, there were about 20% of the DSC applicants actually take advanced module. Today, the number is around 13%. Okay, so, so Professor Mark, if you were a policymaker, how would you energize the students to, take more advanced math? What would you change the way we teach in college?
Well, I guess I would like to change your question a little.
Okay.
So the policymakers would be at all levels.
Mm-hmm.
And well, this year, I think at Hong Kong U, we are considering this M1, M2 as part of the credentials. Mm-hmm. So then there's a change of policy at the level of the university.
It's required?
Well, it counts.
Okay.
Yeah. So then, well, give more incentive
mm-hmm.
for them to take these courses, and you see the you see the dwindling of the students, of the size of the set of students being able to take more advanced mathematics at Hong Kong U, or I guess might be the same elsewhere. So you see that problem. So I would advise, of course, I would say that policymakers at all levels at the university would take serious consideration in remodeling their criteria for accepting students. And so as to how mathematics should be taught, it's not just how it's taught, it's how to get people interested.
Yeah.
I think perhaps there are more attractions nowadays in real life than when we were used to be students.
Mm-hmm.
But when we were students, there's a lot of peer communication among peers. So give them time, you can form interest groups. And whether you form interest group is just a question of formality. But if you have people of roughly the same level, they can communicate. And they can exchange their observations or their reading, the things that they learn on reading, on things that might not necessarily be from the school textbooks.
Mm-hmm. Yeah. Actually, I see so many students here. I certainly hope to see that many of you, in fact, all of you, would actually, take some more advanced math modules. This would be, something I think it would be a first step. I also want to comment that Hong Kong U, while Hong Kong U is doing that, we have also done that in HKUST. Now, the advanced math modules were giving extra points for admission. Okay, so I just want many of the students to know. Okay, now let's. I want to go back to the lecture by Professor Leong on the applied math, and so with the explosion today of AI, big data, blockchain, 5G and communication, and many other technologies. Okay, we see everyone talking about the importance of mathematics as a tool for future technologies. I think certainly Professor Leong has spent so much time talking about that. And he, in fact, even talked about Bitcoin mining, which is, of course, a topic of interest to many of you, okay? So my question to both of you is, how relevant is mathematics to real life today? I mean, is this a good time? Many students will be very interested in knowing, is this a good time to really, to learn, to be studying mathematics or to be a math major, okay? What about the job prospect for mathematicians or for graduates in math? But I want to focus also, what about the graduates of mathematics who focus on more foundational side of mathematics, okay? And I also like to hear your view on the future of mathematics, where it's going, for example. So it's a long question, but take your time. Professor Bismuth, maybe I can start from you.
Yes, so I mean, it's fairly obvious that mathematics today, I mean, and generally pure science, is in a sort of hiring crisis for many reasons. First of all, the economic situation has not been, at least in Europe, so good. There were fewer jobs created. And besides, the students have the feeling that by going to what they believe to be easier subjects, they will have an easier life. I think my view on this is exactly the opposite. Mm-hmm. If everybody goes in the same direction, you create yourself a trouble for the future. That's the first point. And the second point is that the training in mathematics, whatever you decide to do later, after you completed your degree, is really an extraordinary school of rigor, of intelligence, of being able to distinguish facts from fake news. All of this is a rare quantity today. So I think the opposite is absolutely true. Mathematicians, people who graduate in mathematics, they don't limit themselves. They will have a lot of openings. And I would even say this for pure mathematicians. I know, for instance, a company in the US where they insist on hiring people who have had some version of abstract training, precisely because they're able to organize the facts and discern what is true from what is wrong. So I think, you know, that the situation for the moment is in some sense difficult. There is also another factor, that the market has become totally international, has become totally worldwide. In any position, you have people from all over the world who compete on the same positions. This has created also difficulties, obviously. It's not as straightforward as it was, let's say, when I was a young person to get a job now. The level of competition has gone up. But globally, I would say that it makes a lot of sense to still be now a mathematician, to learn the real scientific facts the hard way, and not be intimidated by what others tell you.
Professor Ma?
Well, maybe I can say something about the reality of this part of the world. So actually, I have friends who were in finance, and the person I'm thinking about is actually somebody who has some math background. And when he interviews candidates, the first thing he would ask would be in mathematics. So in certain the sectors in Hong Kong, financial sector, the knowledge of mathematics, the rigorous training in mathematics is considered a big plus. So I think if you think about undergraduate training is for you to broaden your horizon, for you to have intellectual pursuit, for you to develop your talents. So just developing your talents within this period of time is very worth your efforts, and it will also tell you a number of possibilities after that. So of course it is not, but it's quite well known that in certain departments, students who opt to do finance after doing mathematics have easy access to the job market in Hong Kong. So that's one thing that I can tell from real experience. The second thing is that how mathematics is regarded is a societal thing. So it depends on the society, the community. And I think to some extent, from my experience in mainland China, for instance, the respect for mathematics is better than it is at this current moment in Hong Kong. So it might be due to the fact that in Hong Kong, people are more practical-minded. But the general public might not be aware of how things develop in the future. So with more investment into the maybe phenotype or maybe to AI, and there will be a lot of the basic economic activities that are mathematics-based. I would not see pure mathematicians or pure mathematics as being opposite to applied mathematics. One must see this, and also with other sciences, as a conglomeration. And there is, without pure mathematics, without the foundation being consolidated and developed, there will be no methods, no new methods produced for practical applications. So therefore, it's not that someone should do everything, but there should be, within any reasonable economic system or human system to that extent, that a certain chain of experts being able to pass information and knowledge from one to another. So in that sense, I think in the digital world or the numerical world, actually mathematics will remain and may actually prosper in the future. And this chain of expertise should be there and will be developed.
Yeah. Thank you. Actually, I also want to add, from my personal experience, I was actually trained originally in applied math, and I studied mostly after graduation as a pure mathematician. Now I'm going back to data science, machine learning. I think Professor Leon also mentioned that for data science, machine learning today, we've been applying machine learning left and right to solve every problem. But we actually don't know what was happening. Okay, it was a black box. And so there is certain factor of confidence in those algorithms we are using. And it seemed to me that in order to make significant progress in understanding what machine learning has been doing, we actually need new mathematical tools, and almost certainly these new mathematical tools will be developed by mathematicians who with very special, very deep understanding of the foundation of mathematics. Okay, so I want to go back to the future direction of mathematics. This is actually also related to what we've been talking about. I actually, a few years ago, I was talking to some prominent mathematicians. They have been telling us that look at the development of many technologies such as 5G and communication, cryptography, and now machine learning. Many of them were spearheaded by engineers and computer scientists who don't really spend that much time trying to understand the foundation of the proofs and things. So in that regard, they also felt that perhaps there's a need in the future of mathematics to be more experimental, in the sense that we, perhaps there's room for mathematics to be less rigorous, as in contrast to what we have been learning, teaching in school today for really the foundational mathematics. So I want to get your view, both of you. So perhaps I can start off with Professor Bismuth.
Yes, that's a very sensitive issue because, I mean, in some sense, I think in mathematics, at least in mathematics I do, it's essential that we know what is proved and what is not proved, what is true and what is not true. So I think the idea that one could get rid of rigor or establishing, traditional truths in the traditional way, I think it's difficult to imagine this. However, in the field of applied mathematics, I think where applications are more dominant, then of course there is not necessarily the need to involve yourself with a heavy sort of long page proof. This, of course, it becomes a practical matter. But I still believe that what distinguishes mathematics from other fields is the fact that when it says something or when it claims something, it is true. Mm-hmm. I think that many other fields in science do not work in exactly the same way. The sense of truth can be variable, can change from day to day. At least in mathematics, we know what truth is. So that's one of the strong points of this discipline. But I certainly understand your concern that in applications, maybe, there is not such a need of establishing crystal clear or complete proofs. Mm-hmm. I know my colleagues, some of my applied colleagues, talk to me about this, and they are very upset about this trend of saying truths are irrelevant, we have computers and so on. I think my view would be on the old aspect of it. I still believe that truth is truth, and mathematical theorems need proofs.
Mm-hmm. That's a great answer. Thank you, Professor Ma.
Yeah, I agree with Jean-Michel regarding that mathematics has to be solid and the statement has to be proven. But of course, I also agree that you can make a distinction between the pure and applicable mathematics. When it comes to mathematical modeling, it's not so much a question of rigor, but applicability. And there are, of course, many parameters that one can sort of vary. So, but as far as this so-called experimental and semi-rigorous mathematics is concerned, I think you're talking about the foundation of mathematics. You're not talking about the applied ones, right? Mm-hmm. So, I guess one can approach mathematics in the teaching of mathematics. One can also do some heuristics. So heuristics means might be one can use your adjectives, the semi-rigorous or so on. But this heuristics must be finally consolidated with the use of absolutely rigorous mathematics. Mm-hmm. But the heuristics can be used as a means of leading the students to a certain statement, or leading it to a certain direction of thought. So this is so if you interpret that as simply more interactive way of teaching, I think there's some room in implementing that. But in the final analysis, this must be something that can be backed up with the very solid proof and, in the sense of pure mathematics.
Yeah. Thank you, thank you. Actually, that's both of you give really well thought out answers. I just want to comment on that. I totally agree with what you said, although I see a trend today that given the pressure for publication and pressure for pursuing impact indices, clearly if you're on the more theoretical side of math, sometimes you don't get the kind of citation you would get with something more experimental or more data-driven or more computational. So I hope that the mathematical community would achieve the kind of balance we all wish to see. Okay, so now I see a lot of students in the audience, and so my next question to both of you is, among the students, I suspect also that many of you are aspiring mathematicians. Okay, so here we have two fantastic mathematicians. Okay? So you may have some questions. And let me, in fact, I have seen the questions coming from the audience, some of them. So I'm going to summarize a couple of questions to both of you, okay? So one of them is, is mathematics hard for the student? They want to know, will studying mathematics be very hard, or pursuing a career in mathematics will be very hard? They would probably also be interested in knowing, do mathematicians work together, or they're more like someone locked themselves up in their office and just pouring on their thoughts on a proof, or work as a team, for instance? Okay, so my question to both of you is, do you have any advice for them to help with their future success if they choose to be mathematicians or be in mathematical science? I'm going to start with you, Professor Ma.
Yeah, I was having a discussion with some students before this, actually, and in the same building. And they were asking a number of questions along this line, too. So my advice is this. Well, I'm a pure mathematician, so you have to know your trade, so to speak. So you have to have your ability recognized in some sense, in some way. And therefore, you have to do some soul-authored work, things that you work out yourself completely. And then after some time, when your work has been recognized, and so your expertise is known, then when you collaborate, people have a clear idea of your part in the collaboration. So this is important. The collaboration is synergy between the different partners if they have complementary expertise. So for instance, if I work with a number theorist, I'm not a number theorist, then I appreciate their input into the subject. Of course, that might be working a problem in the interface between number theory and geometry. So people are quite aware of our separate contribution to the work. Mm-hmm. And of course, there's synergy, producing things that would not have been produced by either one of us. Mm-hmm. So then this is sort of win-win situation, which allows you to widen your horizon, but at the same time maintain your identity. Mm-hmm. So this is my advice.
Okay, thank you. Professor Bismuth?
Yes, so I would like to make a generic comment. I mean, any activity which is pursued at the highest level has some elements of difficulty. If you are a professional pianist, violinist, dancer, all these things are hard. They require continuous day-to-day training, difficult, you know, a certain amount of humbleness. I think that to become a mathematician, there is also this element. You have to accept the fact that what you're doing, you're not going to get every day a great result, not every day. You need to have a knowledge of persistence. Be persistent in your efforts. That's also not only a scientific quality, that's a sort of moral quality. You need to try to, you know, to be strong. This is not easy. It is not easy for the pianist, not easy for the musician, not easy for the ballet dancer. Mathematicians, I don't think, are so exceptional in that respect. Maybe it's a slightly, at least pure mathematics, a slightly more lonely experience, although I try to give in my lecture, and Guy Ming Mok also explained that collaborations and cooperation take also a big role. But you should not be frightened a priori from what you don't know. Just try. Give a gentle try. Do not try to prove the Riemann hypothesis the next day. That would not work. Mm-hmm. But I think that comparatively, as far as I can observe in various professions, I think ultimately the mathematicians who have pursued in their career are people who are extremely stable, very in their own life, very resilient, and I think that these are great qualities that also students can try to cultivate in themselves.
Thank you. Actually, I also want to comment that many of you have, when you observe the talks by the three mathematicians, they list some papers. I have observed that not a single one of them was singly authored. They're all collaborative, okay? So I think collaboration is an important part of mathematics. And now I would like to give the remaining time to the students in the hall. So anybody has any question, please raise your, okay. Can we pass the microphone? Yeah, to this lady.
So this question is to Professor Bismuth. So I have, like from the talk, I've known that you transformed the Riemann zeta function into a geometric question problem. So I am curious, what is the mindset behind changing this algebraic whatever problem into a geometric problem? And how can we apply this mindset into our future, like solving other problems alike? Thank you.
Okay, so this is that's a very good question. So these sort of ideas essentially comes from physics. In physics, there is a so-called Hamiltonian-Lagrangian correspondence. That's a well-known thing if you just go a little bit further by studying quantum mechanics, which tells you that when you look at certain questions which come from analysis involving the Plashen, its heat kernel, certain questions, there is a way of reformulating the computation as a computation of a functional integral, as an integral, in this case, over path space or over loop spaces. So my strategy was, of course, inspired by this basic thing coming from physics. But the distinguished route I was pursuing was to say, I'm going to do geometry with these path integrals. In other words, I'm not going to look at them as an analytic object. I will look at them as a geometric object and believe that eventually the results you try to prove in the real world, they are difficult to prove, but eventually their essence is best understood on this side of the picture than the original one. If you like, it's as if you had a Fourier transform. So you have operators on one side, path integrals or geometry on the other side, and you freely commute between the two. Certain questions are easily solved on the first side, certain questions are easily solved on the second side, and the hardest questions are solved by looking at the two sides together.
Oh, thank you. We have time for one last question. So this young lady.
Sorry, my question is that, do you think that Hong Kong in general is a good place for studying math, like pursuing math? Like, is the support in the education system and society good?
Okay, thank you. I think I'm going to ask Professor Mark to answer this question.
Your question is whether Hong Kong, developing mathematics in Hong Kong, is a question that the society should take up, or I don't quite catch.
She was asking whether Hong Kong is a good place to study mathematics.
Okay. Yeah. Okay. So, well, Hong Kong has produced lots of very good mathematicians. So I was referring to my former advisor. He was actually from Beijing. Okay. So it was at a time when there was a lot of very good teachers in Hong Kong, and they teach in high school, but actually they have very high qualification, and they were able to inspire students in high school to learn more advanced mathematics. Now, if you ask whether Hong Kong is a good place to study mathematics, it is up to, in some sense, up to the society as a whole to place, among other things, more emphasis on basic science, and mathematics as part of it. And is Hong Kong able to do it? I think Hong Kong should be capable to do it. So whether Hong Kong is a good place depends on the future. It depends on how much time and how much energy the society is willing to invest into the development of Hong Kong, not just as a financial center, but also as a cultural center. Of course, taking into consideration also various developments on the economic side. I think Hong Kong is capable of doing it, and I guess part of this activity is try to motivate students to go along this direction.
Okay, thank you. Let me just quickly summarize. Hong Kong is a great place to do mathematics. Okay, with that, I'm afraid our time is up, and I would like to thank Professor Bismuth and Professor Mark for this very, very interesting and inspiring discussion. And I'm going to pass my mic to the MC.
Fantastic. Thank you very much, gentlemen. Wow, professors, such a fulfilling day and such a rewarding day for a lot of the viewers